Okay, let's get started. So welcome everyone to another lecture as part of our ID 5130 Parallel Scientific Computing course. So in today's lecture we're going to learn about essentially iterative methods for the solution of system of linear equations. Or essentially a linear system. Okay. So in the last lecture we looked at essentially direct methods, right? Which are nothing but the Gaussian elimination, right, as well as LU decomposition, etc. Right. So essentially we said the direct methods are applicable when you have a dense matrix, right? And we also saw if you have a banded matrix in which the non-zero elements are nicely aligned along the diagonal, then we can apply a variant of LU or Gaussian elimination or the tridiagonal matrix algorithm. And of course we were not able to kind of parallelize this because it doesn't lend itself to easy for parallelization. As a result, we looked at something that is known as the recursive doubling approach or the cyclic reduction in the context of parallelization of the banded solution of banded matrices. Okay, so all these methods, whether it is a banded matrix or it is a let's say if you have a dense matrix, these are, I mean, essentially if you have, let's say, large systems with sparse matrices, okay, cannot be easily solved using direct methods, because direct methods kind of tend to store the entire matrix A, and if there is no banded structure as we saw in this particular case, then storing all the elements of A and trying to calculate using a direct method can be very computationally expensive. So although even if you have a banded matrix, most of the times in the in industry and in academia, the iterative methods are preferred over the direct methods, because iterative methods use kind of less storage, and depending on the case, iterative methods can even be faster than the direct methods. Okay, so the philosophy of iterative methods is basically in the solution of a system of linear equations. So we again start off with Ax equals b, where A is a known coefficient matrix, right, and x tilde is the unknown vector, okay, and b is the known right hand side vector, right, for the solution of Ax tilde equals b. In iterative methods, the general philosophy is that we start with a guess value for the vector x tilde. Okay, so we start off with some guess value, let's call it x tilde 0. Okay, and then this guess value will be improved in a sequence of iterations so as to drive this unknown towards a converged solution. let's call the converged solution as maybe x tilde e, that is basically the exact solution. So we realize that this exact solution is only exact to the machine precision, okay, or within the accuracy that we kind of within the accuracy or tolerance that we prescribe, okay. All right, so so essentially this kind of computation of this unknown vector and in a sequence generally involves a matrix vector multiplication, and this will be a matrix vector multiplication if you have a kind of a dense matrix, okay. Otherwise you can kind of reduce that to a only kind of to reduce that to only involve those elements, only involve non-zero elements if it is a sparse matrix, okay. All right, so now of course because we are now looking for an iterative scheme, we can use the number of iterations, okay, that are required to obtain a converged solution as an evaluation criteria, okay. So you can say, okay, I have a particular method A, it converges in certain number of iterations n, and then I have a particular method B, and then it converges in certain number of iterations m, and so you can kind of compare which is faster. So you can use this number of iterations required to converge to a final solution. We can use that as an evaluation criteria to compare different methods, okay. So of course a method that converges quickly is a better method, and that's what you would like to go ahead with, okay. So some of the examples, some of the basic iterative method examples are basic iterative methods are, as you already know, are the well-known Jacobi method as well as the Gauss-Seidel method, okay. So we have these two. So these methods are also, these iterative methods are also known as in the literature as relaxation methods, because the unknown or the unknown vector at any iteration k plus 1 in kind of some form depends on a combination of the unknown vector that is obtained at a previous iteration, okay. So because it kind of relaxes this previous solution towards a final solution, these are also known as relaxation methods in the literature, okay. All right, now so as we said, relaxation methods depending on the specific problem we are solving can be even faster than the direct solution methods, okay. Of course these are, the Jacobi and the Gauss-Seidel methods are kind of very basic. As a result, they are we will learn them because they are kind of easy to learn and implement, and they share a lot of similarities with other advanced methods. However, these methods, the Jacobi as well as the Gauss-Seidel, are actually not fast enough for practical applications, okay. So if you take a off-the-shelf CFD software or any other software, they would not be using a Jacobi or a Gauss-Seidel as their iterative method, although they will be using a particular iterative method to solve for their system of linear equations that they obtain. However, they will not be Jacobi or Gauss-Seidel, they will be something advanced, okay, so for practical purposes, okay. So however, the Jacobi or the Gauss-Seidel are used as preconditioners, okay, in advanced iterative methods such as conjugate gradient, or a multigrid, etc. Okay, so we will not be probably learning these as part of the course, but we will see depending on the time, but probably they can be good candidates for your maybe for your projects. Okay, so if you want to implement them using either OpenMP or MPI later on, they are probably good candidates for projects. Okay, so these are used as preconditioners for more advanced iterative methods such as conjugate gradient or multigrid, etc. And a variant of the Gauss-Seidel, that is of more a variant of the Gauss-Seidel method, that has more practical let's say application, is known as the Gauss-Seidel successive over relaxation. Okay, so that is basically your Gauss-Seidel SOR method. So we will later on try to learn about this method as well in the course. Okay, so this is somewhat more predominantly used, so that it kind of gives results much more quickly compared to the basic Gauss-Seidel method. Okay, all right. So then let us move on to look at the general how any general iterative method works. Okay, and then we will come back and see how Jacobi method works, and then see if we can write a code for the sequential execution of Jacobi method, and then on see if we can do it, kind of make it OpenMP parallel. Okay, so how does general iterative methods work? So that's the question we try to kind of learn next. So the philosophy of general iterative methods. Okay, so in general iterative methods, essentially you start off with with a solution for your system Ax equal to b. Okay, and then the idea is now, of course, A is kind of difficult to invert, right? So we don't want to invert this thing. Of course, if you invert this, then you end up with a direct method, right? So as a result, we will construct kind of an approximate matrix for A, okay, such that, let's say this is A approximate, such that A approximate is easy to invert. Okay, now that is where the idea lies in. So essentially, if you have a matrix A, you're going to split it up into m minus n. Okay, so where m and n are both matrices, okay, of the same size n by n. Let's say if you have square matrices A n by n, so you're going to kind of write m minus n, where m itself is a non-singular matrix, is a non-singular square matrix. Okay, essentially for which m inverse can be easily calculated. Now this decomposition of the into m minus n is kind of what defines the particular method. Okay, as we said, Jacobi or Gauss-Seidel, etc. Okay, so the particular method is kind of dictated by how we kind of decompose, or how easy it is to invert. That kind of dictates the particular method that we use. So m will be different for Jacobi, m will be different for Gauss-Seidel, and so on. All right. So then, if I write, let's say, the initial guess as x star, okay, if I say x star is a guess value or a guess vector that we started off with, and x exact is the final solution vector, right, that we wish to obtain within the accuracy of the machine precision. Okay, then we can write ax star. Then we can write ax star would be equal to b, right? Essentially, this would not be equal as such, but we basically have a guess value, right? So this is because this guess would not satisfy the value. Okay, so what we mean to say is that you have let's say you start off with some guess value for ax star, then I can split this a into m minus n times x star equals b, right? All right. then the value of m x star can be left on the left hand side, and then the n x star can be taken to the right hand side. Then we can write something like this. Then what we basically have is you have x star equals m inverse n times x star plus m inverse times p. Okay, now we said that it is kind of easy to invert, right? It's easy to invert the M matrix. Okay, so if we in case if you have difficulty realizing that these are equal, you can even say that this is the x exact. Okay, so basically this is the guess value that we started off with, which we can even call it just x. Okay, so ax equals p, and then we have x equals m inverse x plus m inverse p. Okay, now using this particular step, we can construct an iterative scheme. Okay, now how do we construct an iterative scheme? Essentially, you want to improve this guess x, so you want to calculate x tilde in an iteration k plus 1 using a previous value. So that means you want to use m inverse n times x to the power x super k plus some m inverse times b. Okay, so that means you want to improve this solution vector x tilde using existing solution vector x. Okay, so this is basically the construction of the iterative scheme. Okay, all right, so essentially we just obtained this thing. So let us call this m inverse n as your c x tilde k plus m inverse b, let's call it a d. Okay, some other vector d. Okay, then you have x tilde k plus 1 or x k plus 1 equals c x k x tilde k plus d. Okay, then this c here that we obtained is called the iterative matrix or the iteration matrix. Okay, which is equal to m inverse times n. Okay, similarly d is the capital M inverse times b, so this is the right hand side vector. Okay, so now this is how all your general iterative methods look like. So, okay, they all are based on a guess value equals c x tilde k plus d tilde. Okay, so that means you will try to improve upon the guess x k by multiplying it c and adding a d vector, and then you try to get x tilde k plus 1. Okay, now what is the guarantee that this will converge? So essentially we say that this particular method, the iterative method is convergent if if the sequence of iterations that we have, that is x tilde k, as your k goes to 1 2 3 all the way to some number of iterations, it could be some number of iterations. Okay, some iteration max, if it converges only if you are essentially in a limit of your k tends to infinity, your xk kind of reaches your x exact value. Okay, so then we can say that the method is convergent, or in other words, we can say in a limit of k tends to infinity or iteration max, your x tilde k minus x tilde e, okay, in some norm equals 0. Okay, so this is some vector norm. Okay, it can be L2 norm or anything, or L infinity norm or something like that. Okay, so now what is the guarantee that this particular iteration scheme converges? It will only converge if if a property of particular this matrix is guaranteed. So if the spectral radius of this particular matrix is less than 1, then we can say that the particular method will converge. So we are not proving this. This is kind of comes from linear algebra. So if you want, you can kind of look up, but it's kind of really somewhat straightforward. So what is the spectral radius? Spectral radius is nothing but the maximum eigenvalue of the matrix C. So this is basically the maximum eigenvalue of lambda, where lambda kind of belongs to the set of eigenvalues of lambda n. Okay, So if the spectral radius, which is the maximum eigenvalue, if it is less than 1, then we can say that that particular method, then we can say that that particular method kind of converges, and we can use the method to obtain a solution. Okay. All right. So now that is kind of the basic, the philosophy of how iterative methods work. Now let us look at the a particular method that is known as the Jacobi method. Okay, so this is Jacobi iterative method. Now, of course, this iterative method can be applied either for essentially sparse or dense or banded or essentially any kind of matrices. Okay, depending on that, you would have the corresponding allocation and storage of the variables. Okay. All right. So now, as we said, in a general particular method, you are going to split A into M minus N, right? You are going to split into two matrices, M and N, and then in Jacobi method, you have to kind of split is A is split into three matrices, D minus L minus R. Okay. So where D is a matrix that contains the diagonal elements, of matrix A. So if you take out all the diagonal elements and make everything else as 0, that is what your D matrix is. Okay, and then your minus L is a lower triangular matrix. Okay, and then a matrix of A, and without the diagonal elements. Okay. Similarly, your minus R is your upper triangular matrix. Okay, of A without the, of course, the diagonal elements. Because the diagonal elements are already considered in the D, so we would not write it in the L and R matrices again. Okay, so if that is the case, then we can write our formula. That's basically as D minus L minus R to the power 2 times xk plus 1 equals essentially we can send the so in this particular case, D is a diagonal matrix, and then in Jacobi method, D is is kind of easy to invert, right? So M will be considered as D and N will be considered as L and R. So if that is the case, we can write the iterative formula as D times x at k plus 1th iteration equals L plus R, right? We are bringing it to the right hand side, times x to the k, right? Kth iteration plus B. Okay, so that's what we have. That means the iterative formula is xk plus 1 equals D inverse times L plus R, right? Times xk plus D inverse times B. Okay. That means what we have is we have the iteration matrix for the Jacobi method is given by C Jacobi equals this D inverse times L plus R. Okay, so this can be written as Cij elements where I comma j go to 1 to all the way to n, and Cij elements would be equal to minus Aij upon Aii for I not equal to j and then equal to 0 otherwise. Okay, now I have written something. How do we get this? This is very easy to prove. You can just take an example of a matrix A, right? So essentially, if you consider A to be equal to A11, A12 all the way to A1n, A21, A22 all the way to A2n, AN1, AN2, ANn, right? Then you can split this into a D matrix, right? So essentially, your D matrix will contain A11, 0, 0 all the way to 0, 0, A22 all the way to 0, right? and so on, 0 all the way to a n n, right? That's your D matrix. And your L plus R matrix would contain everything but the diagonal elements, and then with a negative sign, because minus L contains the lower triangle elements and minus R, so I'm here writing L plus R. So as a result, this will be 0 minus A12 minus A13 minus A1n. Then you have minus A210 minus A23 minus A2n all the way to 0 here, and then you have minus AN1 and so on, right? So that's your L plus R matrix. So now it is very easy to see, right? Essentially, you have the Cij, which is D inverse times L plus R. So that will be D inverse would be, because this is a diagonal matrix, the inverse would be 1 by A11, right? So that's what this particular term is here, right? It will be 1 by A11, and then each element would contain minus Aij. Okay, so that's very easy to see. Now, if that is the case, what will be the particular iteration method that we have developed here, right? How does this look like? So that is basically D inverse times L plus R. So if I call this as B upon so this will be B upon AII, right? Then I can write in using I and J indices, I can rewrite this particular formula as follows, right? By focusing on these two here, I can write it as my X I, that is the at any iteration k plus 1, the entire vector of xi, that is what I have for I goes from 1 to n, can be written as, right, you have a division by a11, a22, that's basically aii will be divisible throughout the entire two of these things, right? So that will be 1 by aii times you have bi, right, minus you have all these vectors will be multiplied with L plus R will be multiplied with x1, x2 all the way to xn, and these are all evaluated at k, right? So essentially you have that's what this will turn out to be, right? L plus R times xk will turn out to be what? Will turn out to be your minus of this entire summation, right? Minus a12 x2 minus a13 x3 and so on. So this will be aij xj of k, right, summation j goes from 1 to n, and then j is not equal to I, right? That's your equation. And then this is for the solution vector that goes from I equals 1 to 3 to all the way to n. Okay, so that is the essentially the formula for your for the Jacobi method, right? Right, essentially for the entire solution, the entire range that is going from 1 to n, that is the size of the matrix is n by n. Okay, all right, then what we see here is that okay, now coming to the parallel parallelizing this particular method, what we see is that we have a dependency on xik plus 1, that means xik plus 1 depends on xjk, so that means k plus 1 depends on k, and not only that, it depends on all the values, that is j equals 1 to n, right, of xjk, right? That means the values xik plus 1 depend on all values of xik, right, where I goes from 1, 2, 3 all the way to n. But that's not a problem because the memory is kind of shared. So as a result, xik plus 1 can be computed, right? Can be computed in parallel, right? Because these are all independent. As a result, the computations of xik plus 1 are kind of, are because they are independent, they can be done and they can be executed in parallel. Okay. All right, so that's kind of introduces the Jacobi algorithm. Now let us see how do we go about writing a serial Jacobi algorithm, and then see if we can look for parallelizing it using maybe OpenMP. Okay, so in what follows, I might be kind of combining the notation of both Fortran and C. So I'll be writing a kind of pseudocode rather than writing a proper C code. So let us see if we can write a serial Jacobi iteration solver. Okay, a serial or a sequential. All right. So let us say we would like to solve a matrix system, and the size of the matrix system is n equals. Let's say it's very large. Okay, so let's say we want to solve a 10,000 by 10,000 matrix. Okay, so n is 10,000, and let us also set the maximum number of iterations, that is iterations max that we want to carry out would be equal to some number. Okay, let us set it to some 5,000 iterations. I don't know if it will kind of converge in this, but we hope it will kind of converge. Okay, that means we would declare our variables, which is n is the size. That's basically int n equals whatever 10,000, and then you would declare your iteration max equals 5,000, right? And then we also have to now let us say if you can have both possibilities. Either you can have A to be banded, in which case you have only main diagonal and the super and the subdiagonals, or A can even be a sparse matrix or a dense matrix, right? So let us kind of try to consider both cases. So if it is banded, you are only going to store only these values, right? You will have an array for A, array for B, and array for C, which are basically the main diagonal and the super and the subdiagonals. If it is sparse, then you need to store all the values of Aij somewhere. Fine. Okay. All right. Then let us see. Then what you need to do is, if let us take an example of a banded matrix. Okay, and if we are, let's say, in the banded matrix, if we are considering, let's say, a problem with one dimensions, and you have this is your grid that you plan to work with. Okay, and somehow you already know from the given boundary conditions, you know the values of these two values, so you already know what is x1 and xn. You need to calculate what is x2 all the way to xn minus 1. Okay, that means if I look at a matrix with size 1 and n are gone, so basically 2 to n minus 1. If I look at n minus 2 by n minus 2 size, let's say it is composed like this: minus 1, 2, minus 1, 0, 0, 0, 0, minus 1, 2, minus 1, and so on. So you basically have a system like this. Okay, so basically you have the diagonals and the super and the subdiagonals. Okay, all right. Then we have to, or A can even be dense. Okay, so I am just taking both examples. Or A can even be let's say this is A1, this is maybe A2, or it can be completely dense. You have all the elements, so this is Aij. Okay, then of course you have to, in the code, you have to also first fill the right hand side vector B, right? So what we do is we basically write for I equals 1, I less than or equal to n, I plus plus. Okay, so I'm kind of considering, instead of 0 to n minus 1, I'm considering 1 to n. Okay, and then you would initialize your B of I, okay, with some known right hand side values that are there specific to the problem. Okay, so that's your initialization of the right hand side, and you have to also initialize your x vector. So for I equals 1, I less than or equal to n, I plus plus, and then because 1 and n are already known, you would initialize only your the interior values, I less than n. Then you would initialize your x of I equals some 0. Okay, all right. So then what do we need to do? Essentially, we need to write a code for this, in which you start off with a guess value and then keep improving this thing. So we would need a main loop, which is basically the iteration loop, right? Now to begin with, let us say we somehow hopefully converge in some certain iteration. So I have another for loop here. I have for loop for the iterations. I declare another variable, iteration equal to 1, iteration is less than or equal to iteration max, that we have set it to be some 5,000 or something, right? And hope that it kind of converges here, and then you have iteration plus plus. Okay, so this is hope it converges within that iteration max. All right, so that's your main loop, in which we have to now calculate what is the new value of x. That means xk plus 1 needs to be computed. Okay, so that means we have to basically compute xk plus 1 for all the range of I equals 1 to n. So basically you have a for loop for I equals, because the boundary conditions are known, we will loop only from I equals 2 to I less than n, I equal to n minus 1, I plus plus, right? If the boundary conditions are not specified using as x equals, x1 equals something and then xn equals something, if it is not specified like this, rather if a Neumann condition is given in which x1 are not specified, rather they are specified as derivatives or something or so, then you would get even values here also needs to be included. Okay, so essentially the coefficient matrix will get enlarged to include 1 and n as well, depending on the boundary condition. But for now I kind of consider that the coefficient matrix, the system, the problem that is given to us has both Dirichlet boundary conditions. As a result, we can work with only calculation of the solution for the interior points, that is from 2 to n minus 1. Okay, so then for I equals 2 to I less than n, that is 2 n minus 1, you calculate your x new, that's your x k plus 1. So we will also allocate arrays here. So basically x of, you will have a real array x of n as well as x new of n and then b, and either you will have the matrix A n by n, okay, or you would have the coefficients A, B, C, D. Fine, we have all those things. Then x new would be equal to, can be written as, if you have a matrix of this form, okay, minus 1, 2, minus 1, then what would be x new? X new would be equal to, if I follow this formula, x new would be equal to b of I minus, I only have, out of this summation, I only have 3 variables, right? So I have the diagonal element and I have the two, I don't have the diagonal element because j is not equal to I. So I have only the two off diagonal elements, that is I minus 1 and I plus 1, and then the diagonal element will basically be division, right? So that means the coefficient is a minus 1, but there is already a minus here, so this will be plus, and then the coefficient is to be divided is 2, right? That's what we'll get. So as a result, if I work with a tridiagonal matrix of the form shown here, then this will be b of I, right, plus the coefficient is 1, basically minus 1 times minus 1, and x of I minus 1 plus 1 times x of I plus 1 is all I have, and then divided by AII, that is your 2.0, right? Basically that translates this matrix together with this equation into this formula, right? Now I'm only using x here because this is xk, right? So xk is what is the dependence on xk plus 1. So x new equals something related on x. Fine. So this is fine. So I'm first trying to write a serial version. Now if let us say we are let's say if this is the case, if you have a tridiagonal matrix. In case you don't have a tridiagonal matrix, if you have a full matrix, right? So this is the case if you have tridiagonal matrix. If you have the full matrix, then of course you need to, instead of that particular statement here, you need to execute something else. That is basically you will first initialize your x new of I with b of I. Then you need to have another loop for your summation of these quantities, right? You would have another loop, so that will be basically declare another variable called let's say sum equals 0.0, and then for j equals 1, j less than or equal to n, j plus plus, right? And then you would have if I or j not equal to I, right? Then you would have essentially sum plus equals or sum equals sum plus you would have aij star multiplied with x of j, right? Okay, you can use either square brackets or parentheses, whether you use Fortran or C. For easiness, I just used the parentheses here. So that is fine. So that's your sum. Then once you have the sum, this already has a plus in there. So the x new should be x new of I should be equal to x new already contains b. So this is x new minus sum, right? divided by a of I, right? That's basically your formula with a minus of the sum, right? So that's the minus of the sum, and b of I. B of I can even be, it need not be initialized. You can even write it right here as well. Okay, anything is fine. Okay, so once you have this, so that's your end of the for loop. So this particular statement here, these are mutually exclusive. Either you use this or or you use this one, right? Depending on the matrix. Okay, so we understand that. Then once you have these new values that are calculated, what can we do? We have to go to the next iteration. So, but before we go to the next iteration, we can update the values, right? So essentially, update the solution vector, right? So because we have found it for all the for, so let me close this for here. Okay, let me close the for loop. If is closed for okay, so I'll close the for loop as well, so that is closed here. Okay, then update the so this is basically okay, then update the solution vector. Okay, then I can go for I equals to I less than n I plus plus. I would update it to x of I equals x new of I. Okay, that's what we have. And then we also need to see if the residual that we have, okay, is actually 0 or not. So how do we define residual? Residual is basically everything taken to the right hand side. So if you have b minus ax, that's your residual. Okay, so r tilde equals b tilde minus ax tilde. Now of course residual will be only 0 if x equals x exact. Otherwise, if x is any guess value, then b minus ax would give you some non-zero residual. So this residual can be actually used as a stopping criteria. Okay, so as of now I have used the iteration max, but we don't know how many iterations are required a priori. So as a result, you have to modify the code. Instead of the iteration max, you have to give a constraint on the residual. If the residual, if some norm of the residual falls below, let's say some 10 power minus 3 or minus 5, whatever, then you can say that that means the solution is exactly satisfying, to some precision that you specify. Then you can say that you can exit the loop, and then that x tilde that you obtain would be the final solution. Okay, so in order to do that, let me calculate the residual. So calculate the residual. So that means I would initialize residual equal to 0, and then I will use for I equals, I can either use all the elements, or I can even use the boundary interior elements as well. For I equals 1 I less than or equal to n I plus plus. Then we would also initialize, because I would need another ax calculation, I will say sum equals 0.0. I have another sum here. Then I would look for j equals 1, j less than or equal to n, j plus plus, right? That's your loop. Sum equals sum plus aij star xj, right? So this is the new x that is updated, and I'm not having an if condition here. We don't put an if condition here because you want to add all the values. Okay, so once you have this, then you come out, you have the entire sum value. Then your residual r would be equal to or r of I, right, would be equal to so this is actually for r, this is a vector. Okay, fine. So r of I would be equal to b of I minus the sum. Okay, then you need to somehow add the r of I to get a final value for residual. Okay, so I can say residual as another variable. So residual would be equal to for I equals, right, or I can just say I can say that r equals r plus, right? So r equals r plus of b minus sum. That will basically give me a final value for the residual, which is a scalar. Okay, that's fine. So basically we have a residual. Now this residual can be used to basically check for convergence. Okay, now let us see how can we actually parallelize this using OpenMP. Well, parallelization is straightforward because we said that all the computations within one particular K can be made are independent. As a result, we can parallelize this thing. So first of all, what is the value? So we started off with the B. So this can be parallel. So this will be, let's say, hash pragma OpenMP, right? This can be filling can be parallel for, right? And then I will be, of course, private. So private variable I, right? And the same thing can be repeated even for the initialization. So this is also hash pragma OMP parallel for private I. Okay, so this is either or exclamation dollar OMP do, if this is a do loop for Fortran, OMP parallel do private I, right? If you are working with Fortran, exclamation dollar OMP parallel do, and then you have private I. Okay, and then of course you need to have the corresponding exclamation dollar OMP and parallel do. Okay, of course. All right. If it is C, you don't need it. Okay. All right. Then what about the main function? Okay. So here we have. Can we parallelize the iterations? The outer iterations. The outer iterations cannot be parallelized, right? Because unless you know on what particular iteration value, you cannot go to the next one. So this cannot be parallelized, but the inner ones can be parallelized, right? So as a result, I can write, let's say, hash pragma OMP parallel. I can fork the threads here, or you can fork it outside as well. And then I would have the private variables as I. Okay. Then I can have hash pragma OMP for, right? So that would be a for loop for the parallelization. Then I have, of course, all these variables. Now sum is, if it is declared if it is declared outside, then of course sum would also be a a private variable, right? Because each thread will calculate its own sum, and then this will come out to be used here, right? So this needs to be used as well here. So sum would also be a private variable in case you are dealing, if you're doing this way. So sum I comma sum, if you declare it inside anyway, it will be automatically private. Okay. And then do we need any other clauses here? So that means the outer loop, this one is parallelized. This one will still run in serial, right? It has to, because you have to add all these values, and then you would get the new solution vector. And then now we are still inside, as long as you are inside this iteration block, you are still fork the thread. So this is only in parallel. Then all the threads will come here. They will also update the solution vector. So this also can be made into parallel. So this can also be hash pragma OMP for. So the copying can also be happen in parallel. Then of course we have the calculation of the residual. So here also you can put hash pragma OMP for, right? This would be a parallel loop. And then what about the variables here? What needs to be so if you have, then this will be okay. Sum is already declared as private and I, so we don't have to declare it again. So because it is reused here. What about R? R is basically now being added, right, by all the threads, because this is all these are all happening, and then this is a reduction operation, right? So as a result, either you put a critical statement, but then we know that a better one to do is basically OMP for. You can have a reduction, right? Reduction is plus, and the reduction variable is R. So the residual will be a reduction operator. So you will get the residual for all the threads together. Okay. So once you're done, then you can kind of output what you found using a you can only let one of them kind of print it. So you can have hash pragma OMP, either the master or the single you can use, and then print the values value of residual as well as the iteration to the screen, right? All right, so then where are we in the program? So this is done, iterations has to be closed, right? So iteration has to be closed, fine. Then until then your forking kind of doesn't close. All right, so of course I have used these iterations here. Now what you can do is, of course, you cannot, anyway you're not parallelizing this thing, so as a result you can even make this as a while loop, right? And then see if you are, execute this while your residual or absolute value of residual is still greater than 10 minus 4 or something. If it is greater than that, you keep doing this while loop, okay? So it can be like that. And of course we probably would need an absolute operator here so that it doesn't become minus. All right, or you can even go for a square of this value. I think this is fine, okay? You can work with this. So that is how you can write a simple Jacobi iterative method in serial as well as in parallel. Of course, somebody has to tell you what is the matrix, and once you know the matrix, you can run this for any number of any size of the matrix, and then for so many iterations until it converges, okay? All right. Okay, so we will pick up from here. I think we are out of time. I'm going to stop here. We will pick up from here in the next lecture. Okay, thank you.